our channel Knowledge Hub. Friends, subscribe to our channel and click the bell icon for the latest update. Today we're going to start with your chemistry for class 12, and this is your class 13. As you know that we had done your class 12 in the last classes, and that we had done your which is in the same cases we talk about it. We had completed unit 1, unit 2, unit 3 and unit 4 in the last class. Now we'll have to start discussing about unit 5, which is your surface chemistry here, that even though we have to discuss about it, and that is also an important one here. Before starting with this, it's a huge request from my side to all the viewers to please go through the subscribe button and please like, share and subscribe our channel, so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. In all about that is talking about surface chemistry here, that some of the important most important chemicals that are products that are industrially by means of reaction that occurs on the surfaces of solid catalysts as well. In terms of surface chemistry, if I'm going ahead, so yes, surface chemistry deals with phenomena that occurs at the surfaces or interfaces, and the interfaces or surfaces that is represented by separating the bulk phases by a hyphen or a slash. For example, the interface between a solid and a gas that may be represented by solid, gas or solid liquid, a gas here, solid slash gas, you can write it down. Due to the complete miscibility, there is no interface between the gases, and the bulk phases that we come across in surface chemistry may be pure compound or solution. The interface is normally a few molecule thick, but its area depends on the size of particles of bulk phases. Many important phenomena noticeable amongst these being that corrosion and electrode processes, heterogeneous catalysis, that dissolution and crystallizations occurs at interface. The subject of surface chemistry finds many application in industry, analytical work and a daily life situation as well. In the same cases, that to accomplish the surface studies that is meticulously, it become imperative to have a really clean surface and a very high vacuum of the order of 10 to the power minus 8 to 10 to the power minus 9 Pascal, and it is now possible to obtain the ultra clean surfaces of the metals. Solid material with such clean surfaces need to be stored in vacuum, otherwise these will be covered by molecules of the major component of air, namely dioxygen and dinitrogen as well. On the same here, for that in this unit you will be studying some important features that the surface chemistry, such as adsorption, catalyst, and of course the collide that includes the emulsions and gels as well. On the same cases, we'll first start discussing about the adsorption here, and that is also an important one. So in the terms of adsorption, which is important and you have to be considered about it, let's go ahead. In terms of adsorptions here, there is that a surface adsorbent or adsorbate adsorption has been take place, and to absorb has a surface like base like solute that we have, and with the same case, if both adsorption and absorption, then it is known as sorptions here. So for that we will discuss here in the detail, but for talking about the adsorption here, there are several examples which reveal that the surface of solid has the tendency to attract and retain the molecules of the phase with which that comes into contact, and these molecules remains only at the surfaces and not go deeper into the bulk. The accumulation of the molecule that species at the surface rather than in the bulk of a solid or a liquid is termed as adsorption, where the molecular species or the substances that which concentrate accumulate at a surface is termed as adsorbate, and that the material that surface of which the absorption takes place is called adsorbent here. Adsorption is essential a surface here that is here that essentially a surface phenomena, and solid particularly is finely divided state that have large surfaces area, and therefore that is your the charcoal, silica gel, aluminum gel, and clay colloids and metals is finely divided into states and act as a good absorbent as well. Now we'll talk about the adsorption in action. Adsorption in actions here. So on the same cases with the same case here, that is with if a gas like O2, H2, CO and Cl2, NH3 and SO2 is taken as a closed vessel that containing the powdered charcoal, it is observed that the pressure of a gas in a closed vessel decreases and the gas molecule concentrate at the surface of the charcoal. That is, the gas are adsorbed at the surface as well. The next, we'll talk about the second adsorption in action, that in a solution of an organic dye, say methylene blue, which when animal charcoal is added and the solution is well shaken, it is observed that the filtrate turns colorless and the molecules of the dye thus accumulate on the surfaces of the charcoal, that is are adsorbed as well. The another, that aqueous solutions of raw sugar here. So on the same cases here that we have here is your that the aqueous solutions of the raw sugar when passed over the beds of animal charcoal and becomes colorless as the coloring substance absorbed by the charcoal as well, and that is the air becomes dry in the absence of silica gel because of the water molecules that get adsorbed on the surface of the gel as well. It is clear from the above example that solid surfaces can hold the gas or liquid molecule by the virtue of adsorption, and the process of removing an adsorbed substance from a surface on which it is adsorbed is called desorption as well. Now we'll talk about the another heading that we have to talk about it, which is the distinction between adsorptions and absorption. Distinction between adsorption and absorption. So the distinction between adsorption and absorption that we have to deal with it here in this, that in adsorption the substance is concentrated only at the surface and does not penetrate through the surface to the bulk of the adsorbent, while in absorption the substance is uniformly distributed throughout the bulk of the solid. For example, when a chalk stick is dipped in ink, that the surface retains the colors of the ink due to the adsorption of that colors molecule, while the solvent of the ink goes deeper into the stick due to the absorption as well. And breaking the chalk stick, it is found to be white from inside, and a distinction that can be made absorption and adsorption by taking an example of water vapors as well. Like water vapors are absorbed by the anhydrous calcium chloride but adsorbed by silica gel. So in other words, we can say that in adsorption the concentration of the adsorbate that increases only at the surface of the adsorbent, while in absorption the concentration is uniform throughout the bulk of the solid as well. In the same cases, we'll talk about the mechanism of adsorption here. Mechanism of adsorption Mechanism of adsorption, we'll talk about it. So here, that the adsorption arises due to the fact that the surface particles of the adsorbent are not in the same environment as the particle inside the bulk and inside the adsorbent. All the forces acting between the particles and are mutually balanced, but on the earth surface that the particles are not surrounded by the atoms as well, or molecules of their kind on all sides, and hence they possess unbalanced or residual attractive forces. These forces of the adsorbent are responsible for attracting the adsorbate particles on its surfaces, and the extent of the adsorptions increases with increase of surface area per unit mass of the adsorbent at a given temperature and pressure as well. Where another important factor that featuring the adsorptions is the heat of the adsorption as well. During adsorption, there is always a decrease in residual forces of the surfaces, that is, there is a decrease in surface energy which appears as heat, and adsorptions therefore is invariable and exothermic process. In other words, that delta H of adsorption is always negative, and when a gas is adsorbed, that the freedom of movement of its molecule becomes restricted, and this amount to decrease in the entropy of the gas that after the adsorption here, that is the delta S is negative here. In terms of adsorption, that adsorption is thus accompanied by decrease in enthalpy as well as decrease in entropy of the system here. For a process that to be spontaneous, and that the thermodynamic requirement is that at a constant temperature and pressure the delta G must be negative, that is, there is decrease in the Gibbs energy on the basis of the equation where delta G we have which is delta G is equals to delta H minus T delta S here. In the same cases here, for that the delta G can be negative, and if delta H has sufficiently high negative values, as you know, the approximation of minus T A S here, T delta S that we talk about it, so that is positive, and thus in an adsorption process which is a spontaneous, and a combinations of these two factors make delta G negative as the adsorption here, and that proceeds, and delta H becomes less and less negative. Ultimately delta H becomes here that equals to the T delta S, and the delta G becomes 0 at the state equilibrium is attained here. Now we'll talk about another question, another type of the topic that we have to discuss here, which is the types of adsorption here. So what were the types of adsorption that we have to discuss, and in the same cases we have to discuss about the characteristics and many more things related to it. So types of adsorption, will go ahead. Types of adsorption that we have discussed. In terms of types of adsorption, there are mainly the two types of adsorptions of gases on liquid solids, and if the accumulation of a gas on the surfaces of the solid occurs on account of the weak van der Waals forces, the adsorption is termed as a physical adsorption, and or we can say that the physiosorptions, and that when the gas molecules or the atoms are held to the solid surfaces by chemical bond, and the adsorption is termed chemical adsorptions or chemiosorption as well. The chemical bond may be covalent or ionic in nature. That chemiosorptions involve a high energy of covalent or ionic in nature. Chemiosorptions involves a high energy of activation and is therefore often referred to as an activated adsorption. Sometimes these two processes occur simultaneously, and it is not easy to ascertain the type of the adsorption a physical adsorption at low temperature that may pass into the chemisorption as well as the temperature is increased. For example, the dihydrogen is first adsorbed on nickel by van der Waals forces, and molecules of hydrogen then dissociate to form hydrogen atom, which are held on the surface by chemisorptions as well. Some of the important characteristics of both the type of adsorption are described here. So we'll talk about the characteristics here. Characteristic that we have to discuss here in the same cases, the characteristics of physioptions as well. You can see that. So in terms of characteristics of physioptions as well, that we even have to discuss about it. So where in this the first we have is your lack of specificity. The first characteristics we have lack of specificity. So lack of specificity here, that a given surface of an adsorbent does not show any preferences for a particular gas, as a van der Waals forces are universal as well. So here no specific catalyst or metal here. The second is nature of adsorbate. Nature of adsorbate. In terms of nature of adsorbate here, that the amount of gas adsorbed by a solid, that depends on the nature of gas. In general, easily that in liquefiable gases, example your with higher critical temperatures, that are readily adsorbed as van der Waals forces that are stronger near the critical temperatures. Thus the 1 gram of activated charcoal adsorbed that more sulfur here, sulfur dioxide, which is the critical temperature is 630 Kelvin, then methane and critical temperature like 190 Kelvin here, which is still more than 4.5 milliliter of dinitrogen, which is critical temperature is 33 Kelvin as well. On the same cases, we'll talk about the third one, which is a reversible nature. In terms of reversible nature here, where physical adsorptions of a gas by a solid generally reversible. Thus we can say that here for this we have an equation as well, and that is in the form like solid plus gas will give gas, or solid plus heat, that we have for the reversible gas natures here. This is from the both side. More of gases is adsorbed when the pressure is increased as the volume of the gas decreases, that is Le Chartier's principle, and the gases that can be removed by decreasing pressure. And since that the adsorption process is exothermic, the physical adsorption that occurs the low temperature and decreases the increasing temperature, that Le Chartier's principle here. We'll talk about the fourth one, which we have to go ahead, and that is the another one is the surface area of adsorbent. Surface area of adsorbent. In same cases for the surface area of adsorbent here, that the extents of adsorption that increase with the increase of the surface area of the adsorbent, and thus that the final divided metal and the porous substances having a large surfaces and that are good adsorbents as well. We'll talk about the fifth one, which is the enthalpy of adsorption, and that is the last as well. In terms of enthalpy of adsorptions here, where that is no doubt that the physical adsorptions here, that exothermic process, but its enthalpy of the adsorption is quite low, and that is near about 20 to 40 kilojoule mole inverse. And this is because that the attraction between the gas molecules and the solid surfaces is only due to the weak van der Waals forces as well. Now we'll discuss the characteristics of the chemisorption, as we had discussed the characteristics of physioptions as well. So here we discussed about it. That is your characteristics of chemisorption. So characteristics of chemisorption that we have to discuss here, that is even though important as I told you. On the same cases, the first we have for that is your high specificity, because यहाँ पे आपका low specificity था and here it is your high specificity. In terms of high specificity here, that the chemisorptions is highly specific, and it is it will only occur if there is some possibility of the chemical bonding between the adsorbent and adsorbate. For example, that oxygen adsorbed on metals by virtue of oxide formations, and the hydrogen is adsorbed by the transition metal due to the hydride formation as well. The second we'll talk about it, that is irreversibility. In terms of irreversibility, as chemisorptions involves the compound formation that is usually irreversible in nature, and chemisorption is also exothermic process, but the process is very slow at the temperature on account of high energy of activation. Like we can say that the chemical changes like adsorptions often decrease with the rise of the temperature, and physiosorptions of a gas adsorbed at the low temperature may change into the chemisorption at a high temperature, and usually the high pressure is also favorable for the chemisorption as well. We'll talk about the third one, which is the third characteristics we have, and that is we have here is your, that is the surface area. In terms of surface area, where that like physical adsorption, the chemisorptions increases with increase of surface area of the adsorption as well. And we'll talk about the fourth one that we have is your enthalpy of adsorption. In terms of enthalpy of adsorption here, enthalpy of chemisorptions is high, like 80 to 240 kg mole inverse, and as it involves chemical bond formations as well. Now we'll discuss about the comparisons of physiosorptions and chemisorptions here, and that is even though important here. Comparison between physiosorption and here chemisorption, that we have to talk about it. So in the same cases here, for the physiosorption it arises because of the van der Waals forces. For the chemisorption it causes by the chemical bonding formation. Here it is not specific in nature, it is highly specific in nature. It is reversible in nature, it is irreversible. It depends on the nature of a gas. More easily liquefiable gases are absorbed rarely. It also depends on the nature of gas, and gases which can react with the adsorbent, that shows the chemisorption. Here it is that enthalpy of adsorption is low, where 20 to 40 kg mole liter inverse in the case, and here the enthalpy of the adsorption is highly, that is your 80 to 240 kg mole liter inverse in the same case. wherein this that the low temperature is favorable for adsorption. It decreases with increase of temperature. In this, that is the high temperature is favorable for adsorption. It increases with the increase of that is your the temperature here. In this, no appreciable that activations energy is needed, and here the eye activation energy is sometimes needed. It totally depends on the surface area, and it increases with an increase of the surface area, and it also depends on the surface area, and it too increases with an increase of the surface area as well. It results into the multimolecular layer on adsorbent surface under the high pressure. It results into the unimolecular layer here. That is nearly about we had discussed the differences between the physiosorptions and the chemisorption, and even though you can write it down for that, because that is also an important one, and you can they can ask you and you can just write it down, all these differences between the physiosorptions and the chemisorptions as well. Now we'll discuss the adsorption isomerism. So that is adsorption isotherms. So adsorptions isotherms, they are the variations in the amount of gas that adsorbed by the adsorbent with the pressure at constant temperature that can be expressed by means of curve that is known as termed as adsorption isotherms, and that is the Friedrich adsorptions isotherms, that is the Friedrich in 1909, that gave an empirical relationship between the the quantity of gas adsorbed by unit mass of solid that adsorbed and pressure at the particular temperature. The relationship that can be expressed by the following equation, and that for that the equation we have as follows is to be x upon m equals to k dot p 1 upon n, where n is greater than 1 here. And on the same cases here, that we have where x is the mass of the gas that is adsorbed on mass m of the adsorbent at pressure p, where k and n are the constant which depends on the nature of the adsorbent and the gas at a particular temperature. The relationship is generally represented in the form of the curve, where mass of the gas adsorbed per gram, that is the per gram of the adsorbent, is plotted against the pressure, and these curves indicates that at a fixed temperature there is decrease in the physical adsorption with increase in temperature, and these curves always seems to approach the saturations at high pressure. So here for that we have a graph that will be representing here. Here that we have, this is x upon m, which is we have, and the graph is to be as follows. This is at 273 Kelvin, this is at 244 Kelvin, and this is at 195 Kelvin. Okay, this is to be as follows here, and this is an adsorption isotherm, and taking the logarithm for both sides in this particular equation, will be having log x upon m equals to log k plus 1 upon n log p. So the validity of the Friedrich isotherm that can be verified by plotting log x by m on y-axis ordinate and log p on x-axis abscissa. And if it comes to be a straight line, the Friedrich isotherms is valid, otherwise not. The slope of the straight line that will gives you the value of 1 by n. The intercept on the y-axis that gives the value of log k. Friedrich isotherms explain the behavior of adsorptions in an approximate manner, and the factor 1 by n that can be the values between 0 and 1. Probable range of 0.1 to 0.5. Thus the equation that we have that holds goods over in a limited range of pressure as well, and that will represent it here. This is B, A, this is Q, where slope equals to 1 upon n, and this is log K intercept, we can see that. And this is your log P, and here it is your log x by m that we have represented on this. And this is a fruit dish, that is isotherm. Here, so on the same cases, these were varying from one to another, and that is for the different scientists what they had investigate, and that what they had find it out. So on the same cases, these were to be as follows, and you have to consider about it. Now for when 1 by n is equals to 0 and x by m is a constant, that the adsorption in the independence of the pressure, and when 1 upon n equals to 1 and x upon m that we have here is that is your equals to P, then of course the adsorption varies direct with pressure here. Okay, directly with the pressure. So both the conditions are supported by the experiment results, and this the experimental isotherms always seems to approach the saturations high pressure, and this cannot be explained by the Friedrich isotherm, and thus it fails at high pressure here as well. Now we'll go ahead with another one that we'll talk about it, and which is the another topic is your adsorptions from solution phase here, that even though we have to discuss here. Let's go ahead for that. Adsorption from solution phase. So adsorption from solution phase, that we have to go ahead, and that even though we have to discuss here as well. Here we go ahead, and on the same cases for the adsorption from the solution phase here, that solids can adsorb solutes from the solution, and also when a solution acetic acid and water is taken with charcoal, so a part of that adsorbed by the charcoal, and the concentration of the acid decreases in the solution. So similarly, the litmus solution when shaken with that is your the charcoal, that becomes colorless. The precipitate of MgOH2 that attains blue color here, and when precipitated in presence of magnesium reagent, that the color is to the adsorptions of magnesium as well. And in the same cases that we talk about it, and with the magnesium as well, and in the same reactant here. So the color is adsorbed to the magnesium, and that the following observation that has been made in the case of the adsorption from the solution phase as well, that observation has been seen that the extent of adsorption decreases with an increase in temperature, and that extent of adsorption increases with an increase of surface area in the solution, that is the surface area of that absorbent as well. And that is the third observation. It will see that the extent of the adsorption depends on the concentration of solvent in solution, and of course that is the fourth observation is been seen that the extent of adsorption depends on the nature of the adsorbate and the adsorbate as well. So the precise mechanism of adsorptions from the solution is not known, and Friedrich equations approximately describes the behavior adsorption from the solution, with difference that instead of pressure, concentration of the solution is taken into the account here. On the same cases, for the same references, the equation as I told you is then x upon m equals to k C 1 upon n, where C is the equilibrium concentration, and when adsorption is complex, that is you are completely on taking the logarithm of the both above equation, then we have your that is log x upon m equals to log k plus 1 upon n log C here, that we talk about it. And on the same cases, plotting the log x by m against the log C, and a straight line is obtained, and which shows the validity of the Friedrich isotherms, and this can be that is your that is tested experimentally by taking the solutions of different concentration of acetic acid, and equal volume of solutions are added to the equal amount charcoal in different flasks. The final concentration to determine the each flask after the adsorption, that the difference in the initial and the final concentration that give the value of X, and using the above equation the validity of the Fruit-Ledge isotherm that can be established here. Now we will discuss application of adsorption as well. Application of adsorption. In terms of application of adsorptions here, the phenomenon of the adsorption that finds the numbers of application that is important there are. So they will discuss the important ones that to be discussed here. The first we have is the production of high vacuum. Production of high vacuum. So production of high vacuum here, that the remaining traces of air that can be adsorbed by the chemical from a vessel that is evacuated by a vacuum pump and is to give a very high vacuum. That is the production of high vacuum, and that is the first application of adsorption here. The second we have is that is the gas mask. In terms of gas masks here, that the gas mask is a device which consists of activated charcoal or mixture of adsorbents, is usually used for breathing in charcoal mines and breathing in coal mines to adsorb poisonous gases as well. We'll talk about the third one, which is the control of humidity. So in control of humidity here, that the silica and aluminum gel that are used as adsorbent for removing that moistures and controlling the humidity as well. We'll talk about the fourth one here, which is we have removal of coloring matter from solution. Removal of coloring matter from solution. Removal of coloring matter from solution. Here, animal charcoal removes colors of solution by adsorbing the colored impurities as well. We'll talk about the fifth one, which is heterogeneous catalyst. In heterogeneous catalyst here, that the adsorptions of reactant on the solid surface of the catalyst increases the rate of reaction, and there are many gases reaction of the industrial importance here that involving the solid catalyst, and manufacturers of ammonia using the iron as a catalyst manufactured of H2SO4 by contact process, and use of finely that is divided nickel in the hydrogenations of oil, that are excellent examples of heterogeneous catalysts as well. We'll talk about the sixth one, which is separation of inert gases. And separations of inert gases here, that is due to the difference in the degree of adsorption of gases by charcoal, a mixtures of noble gas that can be separated by adsorption on a coconut charcoal at a different temperatures as well. We'll talk about the seventh one, and that is in curing disease. In curing diseases, here a number of drugs that are used to kill the germs by getting adsorbed on them. The next is your eighth one, and that is your froth flotation process. In in froth flotation process here, that is a low grade sulfide ore that is concentrated by separating it from silica and other earthy matter by this method using a pine oil and frothing agent that we'll discuss in the next coming unit, even though which we have to discuss here, that we'll discuss in this unit. Next unit is your unit 6, that we'll discuss about it in a detail. We'll talk about the ninth one we have, and that is your adsorption indicator. In terms of adsorption indicator here, the surface of certain precipitates such as silver halides that have the property of adsorbing some dyes like coalescence, fluorescence, etc., and thereby producing a characteristic color at the end point. We'll talk about the 10th one, which is that is a chromatographic analysis. In chromatographic analysis here, chromatographic analysis based on the phenomena of adsorption that finds a numbers of applications in analytical and industrial field here. Now we'll talk about more on the detail about the questions here, which is like the first question of this particular unit is that is write any two characteristics of chemisorptions, that even though I had told you about it, many more than that is your the applications that we discussed about the chemisorption as well. I had told you about the fourth in the detail, so you can just write any two. Why does physiosorption decreases with the increase of the temperature, as I told you about it. And another question is, why are powdered substance more effective absorption than there of the crystalline forms? That you have to explain it out in the form of an answer, and if you are able to, you can just write it down. Yes, I am able to. Otherwise, you can just write it down. I want solution, so that I will be providing you that as well. Now the next topic we'll discuss here, and which is another important topic, and that is in terms of catalysts. So in terms of catalyst here, while potassium chlorate when heated strongly decomposes slowly, giving the dioxygen, and the decomposition occurs in the temperature that is ranged to 653 to 873 Kelvin here. Then we have here for that particular potassium carbonate that we have to talk about it, which is in the same cases potassium chloride, so 2 KCl O3, you give 2 KCl plus 3 O2. However, when a little of manganese dioxide is added and the decomposition takes place at a considerably lower temperature range, that is 473 to 633 Kelvin, and also at the much accelerated rate, the added manganese dioxide remains unchanged with respect to its mass and composition, and in a similar manner the rates of the number of the chemical reaction that can be altered by the mere presence of the forged substance as well. On the same here, for the references we talk about it, where the systematic study of the effect of various foreign substances that rates the chemical reaction that was first made by Berzelius in 1835 that suggests the term catalyst for such substance as well, where in the same case the substances which accelerated the rate of the chemical reaction themselves that remain chemically and quantitatively unchanged after the reaction, that are known as catalysts, and the phenomena is known as catalysis as well. And you have already studied about the catalysis in the functional unit that we discussed in the last unit here. Now talking about the promoters and poisons. Promoters and poisons. in terms of promoters and in terms of poisons here, that we have to talk about it. So there we have to talk about in a detail here, and that is in the same cases, which is also an important one. With the same references, there are many things to be discussed in terms of catalyst here, but we will discuss these one by one. On the same, for the promoters and poisons, the promoters are the substance that enhance the activity of the catalysis, that are, and the poisons decrease the activity of the catalysis here. For example, in halide, that is the Haber's process for the manufactures of ammonia, the molybdenum, that is a molybdenum that act as a process of for iron, which is used as catalyst. And for that, the reaction we have here, which is you have N2 gas plus 3H2 gas, presence of Fe and MO, it will give 2NH3 in the form of gases as well. So now we'll discuss that that is another one is that homogeneous and heterogeneous catalysts as well, and that we even though have to discuss about it, and even though which is also an important one here. So let's go ahead further, and that we have to here go ahead, that is your homogeneous and heterogeneous catalysts. So homogeneous and heterogeneous catalysts, in terms of it, that for talking about the catalysis, that can be broadly divided into two groups, as I told you, the homogeneous and that is the another is your heterogeneous. In terms of homogeneous, if I am going ahead for the homogeneous catalyst only, first we'll discuss about homogeneous catalyst. In terms of homogeneous catalyst here, when the reactant and the catalysts that are same phase, liquid, solid, liquid or gases, the process is said to be the homogeneous catalyst. Following are the some of the examples of homogeneous catalyst, like the oxidation of sulfur dioxide into the sulfur trioxide with dioxygen in the presence of oxide of nitrogen as the catalyst in the Chambers process. So that the reaction for this we have here is 2SO2 gas plus O2 gas will give NO gas here, that is what it will give 2SO3 in the form of gases here. Now this reactant sulfur dioxide and oxygen and the catalyst is nitric oxide are all in the same phases. Now the second reaction we'll talk about it, which is in the form that is the hydrolysis of methyl acetate is catalyzed by H plus ion that furnished by the hydrochloric acid, and then we have CH3 COOH COOCH3, the presence of plus liquid, H2O liquid, it will in the presence of HCl liquid will give CH3 COOH aqueous plus CH3OH that we have. Now we'll talk about the another one, that is where both the reactants and the catalysts are in the same phases here. Now we'll talk about the another one that we have to discuss here, which is the hydrolysis of sugar is catalyzed by H plus ions and furnished by the sulfuric acid here. So for that we'll find it out. So this equation we have for that, C12H22O11 aqueous plus H2O liquid, the presence of H2SO4, it will give C6H12O6 aqueous plus C6H12O6 aqueous. This is glucose, this is fructose, This is solution. This is solution. Both the reactant and the catalyst are in the same phases here. We'll talk about the heterogeneous catalysis as well that we have to talk about. In terms of heterogeneous catalyst that we have to discuss here, and which is also an important one as well. So in the heterogeneous catalyst, that the catalytic process in which the reactant and the catalysts are the different phases that are known as heterogeneous catalysts, and some of the examples of heterogeneous catalysts that are to be given is and oxidation of sulfur dioxide into the sulfur trioxide in the presence of PT, then it is your 2SO2 gases, which is PT gas solid here, which is will give 2SO3 in the form of gases here, where the reactant is in the gaseous state while the catalyst is in the solid state here. Now we'll talk about the another one, which is the combination between the dinitrogen and dihydrogen that to form ammonia in the presence of finely divided iron in the Haber's process. So for that we have here N2 form of gas plus 3H2 in the form of gas will give, this is your Fe, which will give to NH3 in the form of the gases here. So the reactant that are in the gaseous states while the catalyst is in the form of the solid state. We'll talk about the third equation, the oxidation of ammonia into the nitric oxide in the presence of platinum gauge in the Ostwald process, which is 4NH3 form of gas plus 5O2 form gas, presence of Fe only, will give 4NO form of gas plus 6H2O in the form of gas here. So where that the reactants are in the gaseous state while the catalyst in the solid state here. The another we have is your hydrogenations of vegetable oil in the presence of finely divided nickel as catalyst. Vegetables oil plus H2 gas will give Ni, that is solid here, will give vegetable ghee solid. That is that one of the reactant is in the liquid state and the other in the gaseous state while the catalyst is in the solid state here. Now we will be going ahead to discuss about it, which is another one. So let's go ahead for the talking about the adsorption theory of heterogeneous catalysis as well. So here we discuss about the adsorption theory of heterogeneous catalyst here. So adsorption theory of heterogeneous catalysts that we talk about it. In this, this theory explains the mechanism of heterogeneous catalysts. The old theory that is known as adsorption theory of the catalysts, that was that of the reactant in the gaseous state or in solution that are adsorbed on the surface of the solid crystal catalyst, and the increase in the concentration of the reactant on the surface increases the rate of the reaction, where the adsorption that being exothermic process and the heat of the adsorption is utilized in enhancing the rate of the reaction as well, where the catalytic reaction that can be explained in the terms of the intermediate compound formation, and that the theory of the which you have already studied here, where the modern adsorption theory is in the combinations of intermediate compound formation theory and the old adsorption theory. The catalytic activity is localized on the surface of the catalyst. The mechanism involves the 5 steps. The first step we have is diffusions of reactants to the surface of the catalyst, adsorptions of reactant molecule on the surface of the catalyst, occurrence of chemical reactions on the catalyst surface through formations of an intermediate, desorptions of reaction product from the catalyst surfaces, and thereby making the surface available again more reaction to occur. The diffusions of the reactions products that is away from the catalyst surfaces and the surface of the catalyst, unlike that the inner part of the bulk that has a free valencies which provide the seat for the chemical forces of the molecule that are held up there due to the loose chemical combinations of different molecules that are adsorbed side by side, and they may meet that react with each other, resulting in the formations of the new molecules here. Thus the formed molecules that may evaporate, that is leaving the surfaces of that is the fresh reactant molecules as well. On the same cases, this theory explains why the catalyst remains unchanged in mass and chemical compositions at the end of the reactant, and is effective even in the small quantities. That however does not explain the catalytic promoters and the catalytic coefficients as well. So here we have here in the detailed about it that the catalyst surfaces having a free valencies and the catalysts, these we'll discuss in the next coming class here, even though which is important. So first of all, here we'll end up with, and first of all, it's a huge request from my side to all the viewers to please go through with the subscribe button, and please like, share and subscribe our channel, so that many and maximum people can get the information at once, and even you can also enjoy the video as well. Other than that, we had completed your sociology, software engineering, and talking about the chemistry that we are dealing with. Other than that, we are dealing with quantitative aptitude, where in the quantitative aptitude we had started with the arithmetical ability, and in that we had started discussing about we had done your operations on numbers, LCM and SCF of numbers, decimal fraction, and your that is another one we'll discuss about the simplification. Then we had started with square roots and cube roots as well. After that, talking about that, other than that, if I'm going ahead in a detail that we had discussed about it. So yes, of course we had done here. So we had done about it, that is your in terms of reasoning we talk about it. So yes, in terms of reasoning we had started with your that is we had completed your verbal reasoning, which is the general mental ability, and the logic reasoning. And other than that, we had started with verbal reasoning, where we had covered up the series, that is non-verbal reasoning, which is we had completed your series, analogy, classification, and your that is your classification. Then we had done analytical reasoning, mirror image, your water image, and then we had done your that is your embedded figure and spotting out the embedded figure as well. After that, we are dealing with the chemistry of class 12. As I told you, this has been important for the academic as well as for the competition as well, and that is even though important as well. So in the same cases, here we had completed unit 1, unit 2, unit 3, unit 4 and unit 5 we had started with as well, that is of surface chemistry. In the same cases, for the unit 1 that we had covered up, that is the solid state, And in the solid state, we had covered up many more topic like the general characteristics of solid state, amorphous and crystalline solids, and then of course we have your classification of crystalline solid, crystal lasted 10 unit cell, number of atoms in the unit cell, close pack structures, packing efficiency, calculation involving unit cell dimensions, imperfections in solid, electrical properties, magnetic properties as well. In terms of unit 2, which we have to cover up, is your unit 2, that is solution, where we had completed types of solution, expressing the concentration of solution, solubility and vapor pressures of the liquid solution, ideal and non-ideal solution, colligative property, and the determination of the molar masses, abnormal molar masses as well. Unit 3, which is electrochemistry, where we had covered up the electrochemical cells, galvanic cells, Nernst equation, conductance of electric cells and electrolytic cells and electrolysis, batteries, and fuel cells and corrosion. And unit 4, we have to cover up the chemical kinetics, where we had covered up the rate of the chemical reaction, factor influencing the rate of the reaction, integrated rate of equations, pseudo first order reaction, temperature dependence on the rate of the reaction, collision theory of the chemical reaction as well. Unit 5th, which is your surface chemistry, where we had covered up adsorption, catalyst, colloids, classification of colloids, emulsions and colloids around us. Unit 6, general principles of process and isolations of elements, where we had covered up occurrence of metals, concentrations of ores, extractions of crude oil from the concentrated ore, thermodynamic principle of metallurgy, that is electrochemical principles of metallurgy, oxidation, reduction, refining, uses of aluminium, copper, zinc and iron. Then another unit is your unit 7th, which is your P block element, where we have to cover up the group 15 element, dinitrogen, ammonia, oxides of nitrogen, nitric acid, phosphorus, allotropic forms, phosphine, phosphorus halides, oxoacids of the phosphorus, group 16 element, iron oxygen, simple oxides, ozone, sulfur, allotropic forms, sulfur dioxide, oxoacids of the sulfur, sulfuric acid, group 17 element, chlorine, hydrogen halides, chlorides, oxoacids of halogens, interhalogens compound, and group 18 element. The unit 8, we have a D and F block element, where the position in the periodic table, electronic configuration of the D block element, general properties of the transition element of D block, some important compounds of transition element, the lanthanides, actinides, some important applications of D and F block element as well. After that, we have to cover up the last unit, which is your coordination compound, where we have to discuss the awareness theory of the coordination compound, definitions of some important terms pertaining to the coordination compound, nomenclature of coordination compound, isomerism of the coordination compound, bonding in the coordination compound, bonding in the metal carbonylysis, stability of the coordination compound, importance of application of the coordination compound, and of course the coordination compound that we have to discuss here. First of all, it's a huge request from my side to please go ahead with the subscribe button and please like, share and subscribe our channel, so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. Thank you. Hope you enjoyed this video. If you like this video, please give a thumbs up and give a suggestion on a comment box. Thank you.